By episode 03, we have already seen two important truths. AI is not magic, it is a prediction machine, and sometimes prediction can sound confident while being wrong. But there's a deeper question hiding underneath both ideas. Before an AI can predict anything, where did its abilities come from? It did not wake up one morning knowing language, images, code, or facts. Something had to teach it. That teaching process is called training. Training is not a single lesson. It is exposure to massive amounts of data over and over again. Imagine a student preparing for the biggest exam in history, reading libraries of examples, seeing patterns, making guesses, and slowly changing how they answer. The AI does not understand like a person, but training gives it patterns to work with. The data can take many forms: text from books, websites, documents and conversations, images paired with labels, code written by programmers, numbers from tables, sensors, transactions, or experiments. To the model, all of this becomes structured signals. Like rivers flowing into a vast atlas, the data carries traces of human knowledge, habits, mistakes, creativity, and repetition. Training works through a loop. The model sees data, it makes a prediction, the system checks that prediction against the expected answer, then the model adjusts. Think of a musician practicing scales. One note is too sharp, the ear notices, the finger position changes, and the next attempt gets closer. AI training is not music, but the rhythm is similar. Try, compare, adjust, repeat. The adjustments happen inside the model's parameters. A parameter is like a tiny dial inside the machine. One dial might slightly change how strongly one pattern connects to another. Another might affect how a signal moves through the system. No single dial contains the idea of a cat, a sentence, or a law. But together, the dials shape how the model responds. Modern AI models can have billions of these parameters. That does not mean billions of facts stored like flashcards. It means billions of adjustable relationships. Imagine a giant soundboard with more knobs than any human could turn by hand. Training is the process that turns those knobs automatically. Tiny movement after tiny movement, until the machine becomes better at matching patterns in the data. But how does the system know which direction to adjust? It needs a way to measure how wrong the prediction was. That measurement is called the loss function. If the model predicts badly, the loss is high. If it predicts well, the loss is lower. Loss is not emotion. It is a number that tells the training process, you missed the target by this much. Then comes gradient descent. The phrase sounds technical, but the idea is simple. Imagine walking down a mountain in fog, feeling the slope under your feet. You cannot see the whole landscape, but you can take a step in the direction that seems lower. Gradient descent helps the model change its parameters in the direction that reduces loss. Step by step, it gets less wrong. In general, more useful data can improve performance because the model sees more examples of how patterns behave. A child recognizes faces better after seeing many faces in many lighting conditions. A student improves by solving more practice problems, but more data is not automatically better. Repeated, low-quality, biased, or irrelevant data can teach the wrong lessons very efficiently. Training data includes what humans recorded, uploaded, labeled, saved, published, photographed, measured, or wrote down. But it does not include everything. It may miss private experiences, recent events, local context, silent communities, rare cases, or information that was never digitized. The model's map can look enormous and still have blank regions. Every dataset has borders. Because training data has borders, it also shapes behavior. If the data contains bias, the model can learn bias. If the data overrepresents one culture, profession, language, or point of view, the model may treat that pattern as normal. AI learns from human-created material, so it can inherit human gaps. The mirror can be powerful, but it is still shaped by what stood in front of it. There is also a difference between training a model and using a model. Training is when the internal parameters are being changed. Using the model is called inference. During inference, you type a prompt, and the already trained model produces an output. Most of the time, your everyday prompt does not retrain the whole system. You are using the map, not redrawing every road. After broad training, many models go through fine-tuning. If training is the giant library, fine-tuning is the specialized lesson. The model may learn to follow instructions, write safer answers, format responses, solve a particular task, or speak in a more helpful tone. A musician who already knows scales can still train for jazz, classical, or film scoring. Fine-tuning gives direction to ability. Still, data alone does not guarantee reasoning, truth, wisdom, or judgment. A model can learn the style of an explanation without truly checking the world. It can learn the pattern of expert language without becoming an expert. It can learn common reasoning steps and still fail when the situation changes. Training gives the model a powerful map, but not perfect understanding of the territory. A trained model is like a frozen snapshot of patterns from its training process. It may not know what happened after training. It may carry old assumptions. It may reflect the limits of the data that shaped it. That is why AI should be used with curiosity and verification, not blind trust. AI did not wake up knowing things. It learned them, imperfectly, from data created by humans. Understanding that changes how you use it.